Hello guys, welcome back to Mason African Motives, still on industrial electronics info. In this case, we are going to be focusing on AC theory, which is one of the most important topics that you're supposed to understand in your syllabus. So we're not going to waste much time, guys. We're going to work on the revisions that we have from the question paper, which was written in February 2022. That was question number 2, AC theory. We are given the first part, which is one of the easiest questions, but we have to be very, very careful on this one, okay? We're given that an LC circuit resonates at. So here, if we are given that it resonates at, that is the resonant frequency that you're given here. So let's just do this way. So here we are given the resonant frequency, which is 1,2 megahertz. We know that mega means to the exponent of 6. So that's 10 to the exponent of 6 hertz, okay? And a Q of 200. So Q is for the Q factor, okay? That is the quality factor. So we are given that the Q is 200. Calculate the edge frequencies, that is FH and FL. All right, so these are the half frequencies that we have. So the edge frequencies, we know that they are taken from this formula, also from your formula sheet. You can consider that. But in this case, I'm just going to rewrite as it is. Okay, so just a few seconds, guys. Okay. All right, so let's just have this background here. I think it's best for us to have this background. So take note in this case, this is question 2.1. We are given that we have got a resonant frequency of 1,2 megahertz, which I said is the same as 1,2 times 10 to the exponent of 6. Okay, and we are given the quality factor, which is Q of 200. Okay, that is the Q factor. So the edge frequencies, we are referring to FH and FL, which can be taken from this formula. FH equivalent to the resonant frequency plus the bandwidth over 2. So this is actually equivalent to the bandwidth. If it is FL, you subtract this time. So that's FR minus the bandwidth over 2. So this is like I was indicating that here, this indicates or is equivalent to the bandwidth, okay? We know that our bandwidth is actually from our formula, we can calculate our bandwidth, which is FH minus FL. But in this case, we are to calculate this value, so there's no need for us to consider this. So we're going to write this formula as, or it can be written as the resonant frequency over the quality factor. That is the ratio of these two is going to give us the bandwidth in this case, okay? We have these values, so we can just simply substitute into the formula to calculate this bandwidth, which is the resonant frequency of 1,2 times 10 to the power of 6. So that's 1,2 times 10 to the power of 6 over the quality factor of 200. Okay, so let's see what you're going to have. So from your calculator, guys, I want you to simplify properly. You're going to obtain 6,000 in this case. All right. So this is equivalent to the bandwidth. And here we can just write even as bandwidth. It's one and the same thing. So to calculate now FH from the formula that I wrote here, we just need to substitute into this information. So that means our FH here is going to be equivalent to, so that's FR, which is 1,2 times 10 to the exponent of 6 plus the bandwidth over 2, which is we've got a 6,000. So this is a 6,000 over 2. All right, so that's you and your calculator, guys. So I want you to see exactly what we are going to obtain from the calculator. Then after the conversion, I'm just going to write the final answer here. All right, so this is, we can take our calculator here. So we've got 1,2 times 10 to the power of 6, like this, to the exponent of 6, plus 6,000 over 2, which is same as 3,000, or you can write 6,000 over 2 like this. So the answer that we are obtaining here is, you can convert, because this is frequency, we can convert to megahertz, you can convert to kilohertz, depending with what you want to have. Okay, or let me just write it down so that we can do the conversion later on. That's 1, 2, 0, 3, then we've got 3 zeros like that. Okay, So it depends with the conversion that you want to do. If you want to convert to kilohertz like this, kilo means to the power of 3, that's 10 to the exponent of 3. What you're going to do is that you multiply by the inverse, the reverse or the inverse of this, which is 10 to the exponent of 3, like we introduce a negative, which is 1 over this, that's 10 to the exponent of 3. So if you multiply by 10 to the exponent of minus 3, which is the inverse of 10 to the exponent of 3, you are converting to kilohertz, okay? The same thing if you want to convert to megahertz. Mega is 10 to the exponent of 6. You multiply that answer by the inverse of 10 to the x, which means you multiply it by 10 to the exponent of minus 6. Your answer is going to be in megahertz. Okay, so in this case, I'm going to just convert this to kilohertz. So to kilohertz, to convert to kilohertz, I have to multiply by the inverse of 10 to the power of 3, which is 10 to the exponent of 3. So on my calculator, I'm going to multiply by 10 to the exponent of negative 3, like that. So that's 1203. That answer is now in kilohertz. So it's 1203 kilohertz. So that's how you simply convert from your calculator. Okay, let's say you wanted to convert to megahertz. Okay, our answer was like this. Okay, our answer was like this. This was the answer before. So if you want to convert to megahertz, you multiply by the inverse, which is 10 to the exponent of negative 6. That will be something like this, which is 1,203. So it is going to be 1,203 megahertz. Okay, so that's it for the conversion part. I think you understand what I'm trying to say here. All right, then we move on to the lower one, which is now we are going to subtract. So it's FR, which is 1,2 times 10 to the power of 6 minus 6,000 over 2 or 3,000 or 6,000 over 2. So that's it, guys. Just like what we saw from that previous question, we can use our calculator. Again, we are going to obtain something like 1,197,000 like that. Okay, so you do the same, you convert to kilo. So if you multiply by 10 to the power of minus 3 or 10 to the exponent of minus 3, you're going to obtain 1,197 kilohertz. Okay, so that's if you want to convert to kilohertz. So like I said, it depends with your conversion. Do you want to convert to kilohertz or to megahertz? Okay, so that is these are the frequencies that you're going to obtain. Let's check the other part, which is 2.2. We are given a circuit. Then from this circuit, we are given that calculate the total current using J notation. Okay, so that's the circuit there. If you are to check from the circuit, let's take an analysis of what we have here. We are given this is AC. Okay, that's an AC part we have given here. Then you have 220 VRMS, which is the total voltage. 50 hertz, which is the frequency, and the phase angle of 0 degrees, okay? Here we have got the inductance, take note. So for us to have the total current, which means we actually need something like this. The total current is actually equivalent to the total voltage, which is our VRMS over the total impedance of the circuit. But for us to have the total impedance that we have, which means we are supposed to have reactances across the circuit, not the inductance, not the capacitance, but the reactance. So on L3, we are supposed to calculate the reactance here. On C1, which is the capacitor, we calculate the reactance of this one. So this is supposed to be L there. So let's just write it as L3. Then this is C1. The same thing here, we calculate the inductance across this inductor. Okay, the resistances, they're fine like that. So this is what you need. Then from there, we were going to talk about the parallel combination later on. But for the meantime, let's have these. It is going to help us to calculate whatever that you're going to have. Okay, so let's start with L3. Yes, we are not using it for the meantime, but let's just have this in mind that we need this reactance, okay, across L3. So that's XL3, or you can write it as XCL. I don't know the combination that you're going to use on that one. Okay, so that's it. We've got XL3 in this case, which we know that XL is equivalent to 2 pi FL. So that's 2 pi FL. But in this case, we are referring to the inductor 3. So which is 2 pi times the frequency of the circuit, which is, in this case, if we are to check, it's 50 hertz. And the inductance is 155 millihertz. Okay, so millihenries. Okay, so we've got 50 hertz multiply by, we move on to the inductance that we're given. This is our L3. So according to the inductance that we're given, that was 155 millihenries, which is 155 milli means times 10 to the power of minus 3. Okay, so that's it. We can simplify this from our calculator. So guys, I'm not going to waste much time here. From your calculator, you're going to obtain something like 48,695 ohms. Okay, but it's a pure inductor that is the part that we have. It's a purely inductive circuit that we have. So which means we can write this as, remember, it is supposed to be the resistance plus JXL, but we do not have the resistor in this case. So that will be a 0 there. So we are going to have it as 0 plus J 6, that's 48,695 ohms. Okay, so this is what we have as our XL3. So this is the reactance that we are going to use. And you can even convert this to polar form for any sake that you're going to use. You can convert this to polar form, all right? But you can even leave it like that. Okay, then we move on to the C1 and the R2. These two, they are in series. Okay, so that means we can have the total impedance for this series combination, which is a combination of the resistor and XC. Okay, so this was supposed to be, we can write it as Z1. Okay, let's just write this as Z1. So our Z1 in this case, that's R minus JXC, but this is XC for that resistor, for that capacitor, that is capacitor 3, so capacitor 1. Okay, so we can write it as XC1 if you want, or you can just write it as XC, guys. You can even leave it like that, it's fine. But you can just say this is your first impedance. According to the diagram, we are not given that this is the first impedance. So you can actually indicate that this is where you're going to have your first impedance, and here you've got your second impedance like that, okay? So that's you and your diagram, guys, okay? So the resistance, we are going to substitute into the formula. That's our Z1 is equivalent to the resistance that we are given, but we do not have XC. So let's write our resistance of 101. So that's 101. So we're going to have 101 minus J. Then we are supposed to calculate, in this case, XC. Okay, as we can see that XC is needed. So we're supposed to calculate XC, of which XC is given from the formula. All right, that's the formula for XC. That's 1 over 2 pi, which is there on your formula sheet, 1 over 2 pi FC. Substituting the values that we are given, remember that our frequency was at 50 hertz, so it's 1 pi times the frequency at 50 times the capacitance now, which we are given this capacitance as 310 microfarads. So micro, that's 10 to the power of minus 6, or 10 to the exponent of minus 6. All right, so we are going to have this as 310 times 10 to the exponent of negative 6 like this. Okay, so that's your XC here. All right, so from your calculator, guys, if you simplify properly, that's 10,268 ohms, okay? And if it is a capacitor, it is supposed to be, our Z is equivalent to R minus JXC, okay? So that's a minus this time, of which we are going to have this as XC is equivalent the resistance. Okay, we have it there. So, okay, let's just leave it like that. Let's substitute back where we have written here. Okay, minus J I've already written on this part. So we determined XC here, which is 10,268. Okay, so we now have our Z1, which is the total impedance for the resistor and the capacitor that we had. Okay, if we are to check again on the diagram, we have got an inductor and a resistor here. These two are in parallel. I'm going to talk about that later on. Okay, so in this case, we can calculate the total for these two. Okay, But since it is a parallel combination, there is a need that you're going to do to convert these numbers to polar form for when you're multiplying. I'm going to talk about that also. All right, but anyways, let's see what we have for Z2. Okay, so you can even calculate it aside here. So that's our Z2. Z2, that's any resistor and an inductor. So it is supposed to be R plus JXL. Okay, so that's it, of which R is there. So we need XL. So XL, like from the formula that we wrote here, remember our XL is 2 pi FL. So that's 2 pi FL, which is going to be 2 pi times F, the frequency of 50, times L, which is the inductance that we are given on that combination. And on this combination, our inductance is 203 millihenries. Okay, so that's 203 times 10 to the power of milli means times 10 to the power of minus 3. All right, so that's it, guys. You can calculate here XL, which is going to be something like 63,774. All right, if you round off properly here. So now let's take this back into this combination. We've got the resistance here. Our resistance, according to the circuit, that was 89 ohms, if I'm not mistaken. Yes, that's 89. So we are going to have 89 here. So that's 89 plus JXL, which is 63,774 ohms. Okay, so this is the total impedance, like this one in ohms and also this one in ohms. But like I said, for this combination, we are going to combine these two because they are in parallel. So it's best for us to convert this to polar form also here to have our Z1 in polar form, because this Z1 that we see, it's in rectangular form. So we're going to convert to polar form. How do I convert to rectangular form? Okay, so this is, I explained another part that, okay, let me explain again. You need your calculator. So on your calculator, you want to convert to rectangular form. So it's a shift, you press this minus where it's written rec. So rec is rectangular form. So it's a shift rec like this. Then it's 100. You need to insert the values. So it's 101, comma. So the separation of these two, it's shift, then this comma here, shift comma 10. Then for 10,268, you use this normal comma. So it's comma 268 like that. Okay, so that's it. Remember, in polar form, there you are given the values which are in polar form, which are in rectangular form, sorry. So these are the values that are in rectangular form. So from these values, we are given it as X and Y. Why are we given as X and Y? They know that in polar form, we know that our Z, sorry, can be given as X plus JY like this from the indication of the calculus, but X real, then Y being the imaginary, okay? If you are given in a rectangular form, okay, if you are converting to rectangular form, your Z is going to be R angle of theta like this. Okay, so let's see what we got. Okay, actually, I just converted back to rectangular form. Sorry for that, guys. We are converting to polar form. We are converting to polar forms. Very sorry for this one. I hope someone was saying, what is happening here? You are converting to polar form. So to polar form, that's shift here. So it's going to be shift pole. You press the plus there. So as you can see, it's a pole there. Then you insert the values 101. You separate shift at this pattern. That's 100. That's not 100, but 10,268 like that. You close the bracket. Okay. So you are given the value of R and also the value of theta, because polar form, like I explained here, it's R theta. Okay, so our R there is, okay, let's see our R. It's 101,520, but 5 can change this 0 into 1. So it's going to be comma 1 like that. Okay, so that's 105, 101,521 angle of, in polar form, you need the phase angle, which is if you move on this button, okay, if you press this button, it's going to give you the angle theta there. So theta is 5,8. Take note, from your memo there, it was a negative, and that is a wrong, it was a positive. Actually, which is wrong because this is supposed to be a negative there. So the answer that is in your memo there is a positive because they indicated this as a positive, of which it's supposed to be a negative. Okay, so let me insert back here. I hope it is going to work, or let me just redo this with a negative shift all. That was 101. You insert this, so don't forget that negative. Okay, so here that was the most error which was in your formula sheet there. In your memo there is supposed to be a negative like this. Okay, so that's negative 5,8. Okay, so this is going to be negative 5,805 degrees. Okay, so take note here, guys, on this part. Take note on this part here that the value that you are given is supposed to have a negative. We are having a negative on J. So on your calculator, you are supposed to insert the negative, okay? Which is the same thing on this Z2. So on this Z2, you do the same again. We want to convert to polar form. So it's just like what we did previously. Shift, then polar form, which is plus 89. So it's 89. You separate this with shift, then comma like this, which is 63, comma 774 like this. Okay, so this is going to give you R in polar form, which is 109,490. 2 cannot change the 0, so it is going to be 109,490. Okay, here guys, I actually let me show this. I forgot to show the screen, so sorry for that. Okay, guys, I hope now we can see this on the calculator. Let me redo this one. I hope I didn't show this screen. I hope that the screen was showing of which it was. So it's like this. We want to convert to polar form this one. So it's shift, then pol here plus like this, okay? You insert this 89, okay? When you separate this, it's shift, then the comma here, okay? Which is 63, comma 774 like this. Sorry for that, guys. Okay, so that's 109,4. As you can see here, we rounded off, which is just going to remain with a 0 there. Then your theta is 35, comma, which you round off, this is going to be 6234. Okay, so that's your theta. So it's 35, comma 624 degrees. Okay, so that's the same thing that we did on this other part here. Take note on this other part. That's what we did. So I want you to redo and see if you're obtaining the same answer, because the calculator was not showing. I actually thought that the calculator is on the screen. Sorry for that. So that's Z2. Okay, so if we are to check here, we've got our Z2 in Cartesian, which is rectangular form, and also in polar form. Okay, the same thing with Z1 in rectangular form and also in polar form. What's the purpose? Okay, this is what we're going to do here, guys. Remember, I said we are supposed to combine these two, which are in parallel. So we know that for the parallel combination is the product over the sum. Okay, so we're going to have the product over sum of these two impedances that we have. Okay, so let's apply our product over sum here so that we obtain the combined impedance of these two impedances that we are given. So now we can take our formula. So let me just indicate. Yes, seems like we've got a lot, but it's nothing, guys. There's nothing actually. Okay, so ZP, that is the parallel impedance that we have there. That's the product over sum. Remember your formula. So you've got product over the sum of the resistors. Okay, so the impedances that we have, it's Z1 and Z2, okay, over Z1 plus Z2. So like I was saying, that it's very, very important that you work with both calculations in a rectangular form and in polar form. It is best for you if you are multiplying like this to be in polar form. Take note, guys, okay? This can be in polar form. If you are adding like this, it is best for these to be in rectangular form. It is very, very best. Okay, so that's Z1, Z2. multiplying. So we're going to take them in polar form. Remember your Z1 in polar form, that is your polar form. Then your Z2 also in polar form. So you insert these. Let's insert our Z1 here. So that is what you only need, guys. And as you can see, it's a clear indication, okay? So we are going to have our Z1. Remember, that was 101,521 angle of negative. Take note on this negative, guys. That part, I want you to understand it properly. Okay. Then multiply by Z2, also Z2. We are going to take Z2 in polar form. And that was 109,49 angle of 35,624 degrees. Okay, so that's what we have. And like I was saying, it's best for you to add in a rectangular form. So we're going to take Z1 in rectangular form. So our Z1 in rectangular form, that's 101 minus this part, okay? Our Z2 also in a rectangular form. These are the ones that you're going to take. It's best that way because you can simply add them properly, okay? So that's 101, comma, okay, that's 101, sorry, minus J10, comma, 268. So that's 268 plus Z2. Our Z2 was 89 plus J63, comma, 774. All right, so this is what you're going to have. And we know that in polar form, this is the reason, because if you are to multiply in polar form, you multiply the numbers together. Okay, so you're going to multiply these numbers together. In this case, if you multiply these numbers, you're going to obtain something like 111,534. Then what happens with the angles? You add these angles, okay? So if you add these angles, like we said, that angle was a negative, okay? So we actually saw it's negative. So please correct that part that we are having here. So that's 5,805 plus 35,624. Okay, like this. This is going to be 29,819 and so forth. Okay, so this is 28, sorry. Okay, let's check, guys, our calculator. That's 29, not 28, but 29. So that's 29,819 degrees. Okay, then in rectangular form, it's easier for us to add because we are going to add the real parts together. So that's 101 plus 89. So if you add these numbers, we are going to obtain 190 there. So we've got 190. Then the imaginary part, you combine them separately again, minus 10, comma, plus 63, comma, as it is, okay? So you add those numbers separately. So it's going to be 53, comma, so that's plus, okay, 53, comma, 506. All right. So having this now, it in rectangular, in polar form, both, as you can see, it's a combination. On top, our answer is in polar form. Below here in the denominator, our answer is in rectangular form. So you are dividing. When you are dividing, it's best for you to divide in polar form, just like multiplication. It's best for you to multiply in polar form. The same with division. So this is going to force us to change the denominator into polar form. So the numerator is going to remain as it is. So we are going to rewrite this part as it is. That's 29,819 degrees over now this part in the denominator, we convert this to polar form. So like I said, guys, in polar form, that's shift pole, which is shift plus. We have got, okay, let's change here. That's 190, so 190. The comma is shift, comma here, which is 53, comma, 506. We close this bracket. So it's going to give us R in polar form and theta in polar form. So our R is 197. So that's 197,39. Okay. So we put 197,39. Angle of, we are given our theta here. So just move this to the right. That's 15,7277, which is going to be 727. So it's going to be 15,728. If you round off that 7, it will give us an 8. Okay, so in polar form, it's easier to us. Why? We simply have to divide the numbers together. So these two, you divide them separately, which is going to give us 56,313. Okay, what is going to happen with the angles in polar form? In polar form, the angles you subtract. So it's going to be 29 minus 15. So it's 29,819 minus 15, with this number that you're given. So if you subtract, you're going to obtain 14,091 degrees. Okay, so this is the parallel combination that we got in polar form. So this answer is in polar form. So you can convert also this to rectangular. Just know your answers, guys. You never know what's going to happen. Okay, so let's convert this ZP, the parallel combination again to rectangular form. So to rectangular form, it's shift rec, which is shift minus. Then we have got 56,313. Then this to separate the angle, we are going to use shift comma there, which is 14,091. Close the bracket. That's x. Remember, in Cartesian form, we are given x and y. So that's 54,6, whatever that we have, 54,619. Okay, then we move on to the value of y. Y is equal to what? Let's, okay, sorry for that, guys. Okay, I've left the answer there. Okay, let me just redo it fast. All right, that's 56,313, shift there, 14,091. Okay, so that was it like this. Okay, so our y, you move to the right there, which is 13,701. Okay, so you've got plus j 13,701. Okay, so remember, that's Cartesian and rectangular combined. So this is your impedance that we are given, which is the parallel combination. Okay, now let's get back to the diagram. Remember the purpose, we want to calculate the total impedance, guys, the total impedance. Okay, so we're going back to the diagram now. Okay, sorry. Okay, let's get back to the diagram. All right, so that we can clearly see what is left now. So we calculated this combination here, these two, we combine them together. So after combining these, we can see that we are left with this part of XL3, which is now in series to that combination, because it's now a single combination here. So we are supposed to add our XL3, not the inductance, but our XL3, which is when you add, it's best for you to add in a rectangular form. Remember, we calculated XL3. That was the first part that we calculated, if I'm not mistaken. All right, where did we calculate here? Just below here. Yes, we calculated our XL3 here. This is the first part that we calculated. So now we are just going to add, because already we are given this in rectangular form. So we are going to add those two together. All right, so that's what you're going to have, guys. So let's see what you're going to have at the end if we can add these two. So remember your XL3, just remember this value, guys, just remember our value. All right, so that's it. You've got a lot of information. Maybe I can just erase some of the information here. All right, so this is where we are. So we are going to add the two to calculate ZT. So ZT is going to be ZL3, the one that we calculated, plus our parallel combination. Okay, so remember that value that we had, it was, remember, it's supposed to be in polar form, in the rectangular form, which was 0 plus J 48, that was 48,695. Okay, so that's what we had, plus ZP, which is the parallel combination, which is plus 54,619 plus J 13,710. So like I said, it's best for you to add in a rectangular form, okay? Because here we are going to simply add 0 and 54, the real parts together, okay? So if we add the real parts together, we are going to obtain 54,619, all right? We add the imaginary part together, that's 48 and 13,71. So if we add this imaginary together, that will be plus J, it's going to give us 62,619. 62,405. Okay, so this is what you're going to obtain. And this is your total impedance, the one that you're going to use to calculate the total current. But we can convert this to polar form. Remember, it's best for you to, when you are dividing, to divide in polar form. So we can convert our ZT to polar form. This is in rectangular form, so we convert to polar form. So like I said, to polar form, just your calculator, need your calculator here. So that's shift polar form, which is shift plus, we've got 54,619. Then to separate this, it's shift, comma here, which is 62,405, like this. Okay, so we've got our R, which is 82, comma, this 93, and so forth. So we've got 82,931. Angle, which is the angle theta. So our angle theta here, we are given that theta is 48,806. 4 cannot change 6. So it's going to be 48,806 degrees. Okay, so this is our ZT, the total impedance that we have. And the question is to calculate the total current. All right, so therefore, the total current, like we said, is the total voltage over the total impedance, of which our total voltage was 220. That was our VRMS. That's 220 on the circuit, angle of 0 degrees. Then we divide by the total impedance of 82,931, angle of 48,806. Remember what I told you guys, in polar form, you can divide the numbers, these two numbers separately. Okay, so this is what you're going to obtain. 2,653 angle of the angles you subtract. So it's 0 minus 48, which is minus 48,806 degrees. Okay, so this is what we are going to obtain as the total current of the given circuit. So like I said, please take note about that value that I indicated on that capacitor. It was supposed to be a negative, but in your memo there, you see that it has got a positive. That's an error that just happened there. So it actually made everything to be an error. That's the purpose why we bring out these question papers to you guys, so that you can revise, because sometimes you might have an error in your memo and you are wondering what was supposed to be the answer for this one. You are now struggling to figure out the actual answer. So this is the purpose of bringing out these videos to you guys, so that you can also grasp out the actual way that you're supposed to calculate or to work out these questions. But for now, that's what we had, guys, for Meson African Motives on Industrial Electronics N4. Till we meet again.